is it Bill Gates or Jeff Bezos deep learning using Keras tutorial thing. And so last time it was a 30-minute video. There's a lot of content in there. I did create a repo for it, so that's in the video link for all the videos. And I've got some details about the Python version using Anaconda, the version of Keras, and some high-level stuff here so you can follow along. We also have in the folder, I've got the images that I used. I've got the IPython notebook and the Python code for the image scraper, which we used in the video. So hopefully you can use all that to get set up properly. Now let's go back to the code. What did we see last time? We basically saw that we were able to, with around 500 or 600 images of each person, using a deep convolutional neural network trained from scratch, we got what was my best validation accuracy here? It was 80%. Not bad at all. Sorry, I have a little bit of a cold, so that wasn't bad. But the thing is, look at how long it took for each epoch. It took 22 seconds. It took a while, but that's still not bad for such a low volume of data. I wanted to go over another strategy which is pretty popular, and this is not novel to me. I mean, it's all over the internet, but hopefully I can provide a very, very simplistic point of view on it and add some nuances that maybe other people didn't. You can take a neural network that's been trained on recognizing, subject matter that's similar to your domain or maybe not so similar. That's a whole nother story. And you can use the features generated by that network. Now, when I first heard features, that's kind of like, oh, Captain Obvious. What is features? What are these things? And really, with machine learning, a feature is just some numerical representation of anything. So if you have a picture of Bill Gates, you can come up with a numerical representation of what that feature is. These features are also typically NumPy arrays of various dimensions. So this is straight from the Keras website. You can find it. We're going to import the model VGG16. I think I've already imported this. I don't think I'm using this. But in any event, you want to set the model equal to this class invocation. The weights will be imagenet. And if you don't know what imagenet is, it's an academic and nowadays, I think, commercial research competition to predict what class an image belongs to. I think there are 1,000 classes or more. It's a computationally complex thing, and the architectures are very deep, many layers. They run for many epochs. And I don't know if people can really formally verify why they work, but the winner is usually happy to win because then they have, they could do whatever they want because they're geniuses or something. So, but that being said, we've loaded the model. It might take a few seconds because it's going to download something. Now, when you look at the summary, you can see that, the number of parameters here, even when we get rid of like the dense connected layers after all the convolutional layers, don't worry too much about this. We still have 14 million trainable parameters here. We had a fraction of that on the little convolutional network that we built. You can check that yourself. Well, basically, we're going to use this to predict or just output data. So the data is going to be in the shape of something, which will be the number of examples, like 1100 or 100 or however many images we have. And then this will be like something, something, and 512. So basically what we're going to do is we're going to continue to use these generators to get some data. One thing I did want to bring up, so remember how I created the validation set? I took the top 50 images from the folder of each picture, each picture folder, so the Gates folder and the Bezos folder. Now, if the script I used in Python, if those were the first 50 images that came up in the Google search engine, our validation set might be holding the best, most representative images. So did we, really we should have randomized the items in the folder first and then selected the top 50 because we could have introduced some bias there. Typically Google returns the best photos or the more linked to photos, if you're familiar with SEO and the way all that works. So, you know, we could have done something improperly there. And I'll tell you, to be honest, splitting up your validation data and your training data is actually pretty complicated. You know, imagine you're trying to classify music or something, and you're looking at 10-second tracks of a song, and say it's a hip-hop song or a rock song. Since songs are very similar throughout, if you just break up songs into 10 seconds and you have all these 10-second chunks and you just randomize them, the training set and the validation set are going to contain snippets of the same song. So, you know, it's very nuanced. You got to kind of really figure out what are you trying to do and what does it mean to be validation data. Don't just say, oh, I have to randomize something and use some NumPy mask and that'll be it. That's not it. Sometimes, you know, you need to really think about what the hell you're doing because it will screw you up. All right, but on to generating the features using VGG. So since this takes a couple of seconds, I'm just timing it. I'm creating 2 new generators, and I'm just using the train data gen that we invoked up here, which was basically like it takes an image and it applies some minimal transformations to it. And what I'm doing with that here is I'm telling it to look in train images. We're resizing it now to 128 by 128, which is half of the 256 by 256. I figured that might make more logical sense. It may not make any practical sense. I'm going to use batch size of 1, and I'll explain that in a second. Class mode equals none. We're just using this to generate predictions. We're not using it to train anything. And we don't want to shuffle it. Please don't shuffle it because your data will be out of order, and you'll see why that's a problem. So what you're trying to get are probabilities for your training data and probabilities, or not probs really, but you're almost, this is just like data, right? You're just a data set. So I just called it probs. And what I'm doing is model, which is now the VGG16 model with the dense fully connected layers chopped off. We're using a method called predict generator, which is a method on a Keras model. And we're feeding it generators like we did last time. Since the batch size is equal to 1, and I have 1,099 training images, I'm just calling 1,099. I'm setting workers to 3. If you check your CPU while it's happening, you can see what effect that it has on your CPU. It shouldn't do anything to memory, but you can also read the documents about the methods that predict generator takes. I'm using verbose because I want it to print out a little progress bar. Since it took, you know, around 2 minutes or 3 minutes, it's kind of boring. You don't know if it's going to take 3 minutes or 30 minutes sometimes. So at least this gives you a sense of should I wait for it. And it took around 100, you know, just under 3 minutes. So what do we get though? This is the important thing. What are trained probs? What the hell are valid probs? So usually you want to look at a shape. And there's also some notes I have here. I'll go over that in a second. The shape of something is very important. In machine learning, the networks require shapes. You really should know what it is you have. So train probs, which are the features generated from the train images using the chopped off VGG imagenet model. We have 1,099 images. They are in the shape of 4 by 4 by 512. Now 512 right here, right? So basically what's happening here is you can see you got 1,099 images, 100 images, and then the labels are just like it's going to be a 1, 0. So how do you get the labels? So train gen, that has, and you know, the Jupyter Notebook autocomplete's great. You can see the class indices too, Bezos, Gates, and then you can get the classes. And since it goes in order, it first went through Bezos, then it went through Gates, and since we did not shuffle them, it's just a 0 for one guy or a 1 for the other guy. And since we only have 2 classes, we don't have to do any one-hot encoding. I'll cover that in another video, but this is kind of like, if you try to extend this example to more than 2 classes, things will get screwed up because of how you're handling the labels. But for now, we don't have to worry about that. But we could see we have, you know, the shape of the labels is going to be the shape of the examples, right? So you should make sure that your those dimensions match up. Maybe throw in a little assert statement or something like that. But anyway, that's the features. Now, what are these features, right? So this kind of like 4 by 4 by 512D vector matrix thing, it's what is it, right? It's not a sequence like text or audio or time series data. I don't think it really has any like higher dimensional features which might be kind of spatially invariant, like a nose or a face or something that you could visibly say, oh yeah, I see this over here, I see it over there. It's not always in the middle, it's not always on top, but it's a common thing. And so this problem almost falls back into the domain of traditional machine learning algorithms. So, but again, you have the problem, it's not a 512D vector, it's a 4 by 4 by 512D vector. So it's not really, like if you wanted to stick it into a support vector machine or something else like that, you would have to further massage the data. And if you just flattened it out, right? Let's say we took one, let's just look at it. It's this terrible thing, and you know, 4 by 4 by 512. So if you flattened it out, tuple object is not callable. If I ravel it, the shape right there, right? So it's going to be an 8192D vector. So, you know, maybe you would have to PCA that down in order to really use it for an SVM, or so, you know, it kind of lends itself well because it may still be a nonlinear problem. An SVM and a lot of traditional algorithms are linear learners outside of using some kernel tricks. So you know, we're going to take advantage of the neural network because it learns nonlinearities, right? And what the hell does that mean? If you've already seen this, maybe you just skip a minute, but let's say that we have this problem right here. We want to classify, you know, a distinction between the orange and the blue, right? So if you start classifying it, you have this, let's actually get rid of the hidden layers and just try to classify it using two features, right? It's going to do its best. It doesn't have any hidden layers. It's not really going to do anything. If I add one hidden layer, it'll start to improve slightly, you know, or maybe majorly its ability to do this classification. If you give it a more complex problem, you know, is it really classifying that? No, it kind of got stuck in drawing lines above the zero axis there. If we add more layers, does it? So I'm just trying to get the idea that it's a lot of these problems with these 4 by 4 by 512 or whatever it is, you need a nonlinear classifier, something that can approximate the function. So that's why we're not using a convnet, but we are going to use a multi-layer perceptron. And basically, it's kind of like the other model. I'm just giving it a different name, so it's a sequential model. We're going to flatten it. So that's going to basically convert, you know, that 4 by 4 by 512 into something that's probably like that. And then we're going to add some dense layers. We're going to specify activation, use dropout, stuff like that. The dense and activation on sigmoid is still the same. We're going to continue to use Atom as the optimizer. And when you call model.fit train probs, that's just that big NumPy array. Train gen classes is that sequence of zeros and ones. And so we're going to run that, right? And the thing about this is it's going to run a lot faster. We're not doing any convolutions. So it's only taking like 1 or 2 seconds per epoch to run. And we're already at sort of like our original benchmark, low 70%. We did get up to 80 though. And I found after running this a few times, it doesn't really get past 75. You can see we're overfitting. You know, our training accuracy is kind of going up, well, dropping back again, and our validation accuracy is not really improving wildly. And so that's not necessarily a good thing. As you can see here, Let's let it run since it's not going to take very long. Let me see if I had any other notes I did want to bring up. Yeah, the idea of a generator, we've been talking a lot about generators. So in Python, a lot of other languages, sometimes you don't want to have everything in memory. The generator just lets you express your logic incrementally over some data or data structure, and you can do what you want with it incrementally. You know, imagine you had 100 billion lines of text and you wanted to count the number of times the word dog was used. You could just read 101 line at a time and then keep a little counter or data structure incremented every time you saw that word. And the memory requirements for that little data structure would be very, very small compared to the memory requirements of reading in 100 billion lines of text, if you could even read that into your RAM period. So, but yeah, it's a common topic in Python. It's one of the advantages, things people like about Python. It helps you analyze large data sets using a relatively modest computer configuration. And I think we're almost done with this. And yeah, you can see, you know, we're almost at 92% training accuracy, so it's definitely overfitting relative to how it's doing on the validation data set. We got up to 75%. Now, so we had a lot more speed, right? It only took like 3 minutes to generate the data, and it took almost, you know, 1 or 2 minutes to run through all these epochs, which was hardly anything. Now, why did it not do any good here? So my theory is that this is imagenet, right? So imagenet is trying to, let's just look at the categories for imagenet. They have a lot of weird categories, right? Like a hamster, I don't even know, human, face, malamute. I don't know, but in any event, I don't know, you know, one thing I can tell you that ImageNet did not learn to tell the difference between two people that look relatively similar. So keep in mind that they are white, Caucasian. They are, you know, over 50, I think. I don't know much about either of them really. And they are affluent, so they probably wear nice clothing. One is, you know, one isn't walking around with like a tank top all the time, right? So visually, from a discriminative point of view, I can't really say that the ImageNet features are going to be really that powerful versus convnet from scratch. Now, one thing you can do quickly if your model is overfitting and your validation accuracy is not improving is just get some more data. So I may go back, and instead of downloading 500 or 600, we get 2,000. And then maybe we can get our scratch convnet up to 85%, or maybe we can get this strategy up to 80 or 85%. In the last video, we're going to take a look at fine-tuning a network. And this is the most complicated thing, and it's kind of a head-scratcher. I don't totally understand it. But you're freezing some of the layers in the model. You're keeping the weights that they learned up until a point, then you're retraining them. Again, I'm not an expert at this. I just kind of understand how to hack around it a little bit. And it doesn't necessarily mean it's going to work that much better. In the typical dogs and cats examples you see out there on the internet, ImageNet knows about a dog. It knows about a cat. So, you know, the strategy we just used might have actually worked better because the features would have been very doggish and some of the features would have been very cattish. But again, I don't know if those are words, doggish and cattish, but they're probably not. In any event, it's not really clear that given the visual similarities between these two people, I'm sure ImageNet will know that they're people. But, you know, the fact that they're Caucasian, the ages are similar, and they probably wear similar clothing, again, not like muscle tank tops, or, you know, board shorts or funny Western hats. Maybe those aren't enough to discriminate, especially on a small data set. They both have eyes, you know, arms, stuff like that. They might have ties on sometimes. One thing I just thought of here, and I'm not sure if I did a good job with this, is we didn't randomize the data here. So, right, we have everything in order. So I think, let's see if we can, this might throw off the order of things. And this is something that'll happen sometimes, right? So it doesn't appear that adding shuffle as an argument really threw off the ability of, okay, so it is shuffling it now. That's something to be careful of. Sometimes after you spend a lot of time preparing your data, you forget to shuffle it again. So just food for thought there. It does pay to get a little bit familiar with the Keras arguments here, different methods, and whether or not you want to randomize your data, whether or not it makes sense to. So yeah, again, even doing that, we're getting pretty similar results. So hopefully that was kind of useful. In the next video, I think I'm going to get more data and see how we do with this, with a convnet. That'll take a little while to run. I'll use the same strategy, and I'll think about fine-tuning and start putting together some notes around that. So yeah, let me save this after it runs. I'll push it up to GitHub to be the next notebook version, and I'll upload this video. So hopefully this was semi-useful for you guys. If you're worrying about like confusion matrices and trying to figure that out, we'll probably do one of them too in this series. So I'll see you then.